It's part of the business of geology to date rocks, to discover not just how they were made, but in what order and how long ago. If you can't do this, it's like being a historian and knowing about, say, the Battle of Hastings and the French Revolution and World War II, but not knowing when they happened or which came first. Such a situation would clearly make nonsense of history, and as geology is, roughly speaking, the history of the Earth and how it got to be the way it is, rock dating is important. The first very simple and fundamental rule is what geologists call the law of superposition. A rock lying over another rock is the younger. So if in any one place there had been no disturbance, from the surface down at that place there would be a complete sequence of all the rocks ever laid down. So imagine it so from here, in Trafalgar Square. If I take a kind of magical lift downwards, I'll pass through layers of successively older rocks. And what will happen is that I start finding myself among the fossil remains of the plants and animals that lived and died when the rocks were being laid down. So here I go. Remember, fossils are a basic geological tool. We soon leave behind man and all the familiar beasts and meet the tiny ancestors of the horse. Trees look much the same, but there are some weird mammals that are now extinct. You'll notice I'm traveling rather fast because each of these layers or periods represents millions of years. Down in the rocks of 65 million years ago, I'm in the Cretaceous. That's Latin for chalk, among the last of the dinosaurs. The thing is that fossils like these are used to compare the ages of rocks. Whenever the fossils are of the same kind, then the age of the rocks is likely to be the same too. When the whole collection of fossils changes dramatically, the geological period is given a new name. Down in the Jurassic, named after the Jura Mountains, the seas are full of spiral-shelled ammonites. The first bird, Archaeopteryx, is in the air, and it's the heyday of the great dinosaurs on land. In the Triassic, tri because it's got 3 divisions, the dinosaurs are just getting going, though there were lots of mammal-like reptiles, such as the Dicynodonts. In the Permian, early reptiles are in full swing. There's an amphibious reptile called Mesosaurus, and a biggish sailback carnivore called Dimetrodon. And then in the Carboniferous, carbon, because of all that coal, insects like dragonflies are doing very well. There are tree fossils, like those you sometimes find in pieces of coal, and there are crinoids, or sea lilies. And down in the Devonian, first described in Devon, I'm in the age of fishes. It's also the moment when the fish start coming out of the water onto land, so we start finding amphibians. And then I hit the Silurian period, named after the Silures, an ancient Welsh tribe. This is where the first fish appear. And below them is the Ordovician period. The Ordovices live next door to the Silures. This was the age of invertebrates, animals without backbones living in water. There are corals and strange colonial animals called graptolites. Lower still in the Cambrian, Welsh again, I'm back into the period when life first appears in any quantity. There are trilobites in the sea and primitive corals. And finally, below that, in what's called the pre-Cambrian, virtually nothing. 1 or 2 fossils, but life was sparse. And what creatures existed were very small. So, back beyond the 570 million year point to the beginning of the Earth, without any fossils to help, there was little scope, until recently, for sorting out the order in which the pre-Cambrian rocks were made. So, having looked at this imaginary, neat, tidy pile, we must look at how all the layers of the different ages came to be visible to us at the surface. There are various mechanisms. For instance, after a period of deposition, the layers lie horizontally like this, with the oldest at the bottom. And a deposition period may be followed by a mountain building movement that folds these rocks into a great upfold, or anticline. And if I then take this cheese wire to represent erosion, erosion gets to work and slices out the top of the anticline. And then it reveals the oldest rocks in the middle, and they get younger as we come outwards. Well, this kind of thing happened in Leicestershire, in Charnwood Forest, near Leicester, where Dr. Trevor Ford works at the university, and he's been studying the local Precambrian rocks.
Here in Bradgate Park, we're amongst the ancient rocks of Charnwood Forest, which have been dated at about 680 million years old in the Precambrian era. The particularly interesting feature about these rocks is that, unlike most Precambrian rocks, they contain fossils. The first one was discovered some years ago by a schoolboy who was rock climbing. He found this impression on the rock surface and came into my office to tell me about it, and I frankly didn't believe him. But he brought his father back to back up his story, and together we went out to look at this fossil. It turned out to be an impression of an organism we call a sea pen, a distant relative of jellyfish and things like that, still living today, but in this case making an impression rather like a frond in the rocks. I named it Charnia masoni, after the schoolboy, Roger Mason, and similar fossils have been found in many other parts of the world since then, all in rocks of Precambrian age. Another interesting thing about these rocks is that, in contrast to other Precambrian areas, they're only very mildly metamorphosed, so that we can study the detailed structures and see that they were formed from volcanoes erupting in this area. In particular, the lower half of this crag is part of a heavy shower of volcanic ash, which landed in this area, probably landing in water. And as the volcanic eruptions waned and became milder in effect, so we got thin showers of dust grain size ash accumulating one after the other, being deposited in water. But we have this peculiar dimple structure in the layers, and we think it represents where a projectile thrown out by the volcano landed in the relatively soft mud, forming a crater which was subsequently filled in with little pocket-shaped masses of sediment until everything was leveled up again. Now, these rocks were, of course, originally deposited on a flat seafloor, so that they would have been in horizontal layers. But the fact that they are now tilted to something like 45 degrees is evidence of the continual movement that is taking place in the Earth's crust. Elsewhere in the park, we can see the effects of pressure superimposed on that fold. Cleavage is what happens in rocks when they are subjected to great lateral pressures. They are squeezed, and when the pressure is released, they tend to part at right angles to the direction of greatest pressure. And the parting planes are the phenomenon we call cleavage. Now, we can see this in the rocks just round here. We have the original sedimentary layering well displayed here, but round the corner we can see the cleavage very well displayed here as the vertical parting planes in this thin layer of fine-grained rock in between the two coarser layers. Now, of course, these were once all horizontal, but the folding tilted them over to 45 degrees, and then the lateral pressure squeezed the layers together, imposing the cleavage here. Now, if we quarried this layer, it would make thin slabs like roofing slates. But obviously, to be an economic proposition, one would need a very much larger mass. And roofing slate used to be quarried about a mile away from here, up to 100 years ago. Now, these rocks in Charnwood Forest are similar to outcrops in Shropshire, the Malvern Hills and Nuneaton, although dating of these accurately is a very difficult business. All we can say is that they are similar in age and that they are all younger Precambrian. For the oldest Precambrian rocks, we have to go to the northwest highlands of Scotland.
Before we go to Scotland, 600 million years is easier to say than it is to imagine. But we aren't imagining anymore. There are laboratory techniques for measuring these vast ages in a sample of powdered rock. When a rock is made, it contains, amongst its billions of atoms, just a small number that are radioactive. These are unstable and they decay, forming another element in the process, which is stable. We know the rate of decay of the different elements, and so measuring the present proportions of these two, the unstable parent element and the stable daughter element, reveals the age of the rock in its present form, the date at which it crystallized or was changed by heat and pressure. The amounts of these elements in the rock are minute, but repeated measurements give us a reliable estimate of its age. With this kind of dating, we can say that the Precambrian rocks in the southern part of England are all in the region of 680 million years old. The Charnwood Forest rocks are surrounded by younger sediments, and we next find the Precambrian emerging to the west in the Malvern Hills. The Malverns are a long, thin range of igneous rocks that have also been very much altered by heat and pressure at some later stage in their history. So they're very hard to decipher, and they don't appear to be related in any obvious way to any of the other Precambrian outcrops. If we go north, we find Precambrian rocks again in Shropshire. A line of Precambrian volcanic hills runs northeast-southwest along the Church Stretton Fault, and immediately to the west of it we find a sizable Precambrian area of some 35 square miles exposed in the Longmynd. This rock is sedimentary, a mixture of shales and sandstone and grits laid down in water. It varies a lot in texture, from coarse conglomerates to quite a fine-grained structure. You can see it quite well in the broken corner on this weathered, lichen-covered fragment. The Longmynd is in fact a north-south ridge about 12 miles long. It's actually one upturned side of a big downfold, and it may already have stood out as a cliff at the edge of a sea some 450 million years ago. I can quite easily imagine waves breaking there at its foot. Now the Mynd is a long, high barrier, uplifted not against the sea, but against the westerly wind, which makes it a very fine gliding site. The gliders only have to be catapulted off the escarpment and into the hill lift to start soaring. Out to the west again, the Precambrian vanishes underground and provides a basement for younger rocks. We find it again on the coast of North Wales, and particularly in Anglesey, where it's known as the Mona Complex, Mona being the Roman name for the holy island of the Druids, old and heavily faulted, and geologically still not fully understood. Some of the Precambrian rocks show through the surface in rough and weathered crags, and there are some particularly interesting features, like the pillar lavas, which are now protected in the Newborough Warren Nature Reserve. These are lavas that were erupted under or into water, which makes them cool quickly into these remarkable pillow-like forms. At the northwest corner of the island, there's another outcrop that almost certainly marks the site of some old lost ocean floor. These rocks started off as layers of sediment eroded off the land and deposited in the sea. Then a disturbance of the crust has carried them down below the Earth's surface, where pressure and movement have squashed and twisted them into these fantastic folds. Now they've come up again to become these cliffs around the South Stack Lighthouse, facing out into the Irish Sea. In fact, there's a little bit of Precambrian here in southern Ireland at Rosslare, and some geologists think that these two outcrops were connected, part of the same landmass which has since been obliterated by erosion. Back here in the Midlands, these three outcrops that we've seen are the tips of what slopes away beneath the land as a basement, which we know is there under Norfolk and the southeast of England because boreholes show it to be only 100 feet or so below the surface. Up in the northwest, in Ireland and northwest Scotland, we have much older Precambrian rocks. In fact, down here in the south of Britain, all these rocks are of 670 to 700 million year age. But up in the northwest, these pale sediments are as young as 800 million, but by the time we reach the northwest coast, we're actually at 2,700 million years of age. There is therefore a dramatic difference in age between these northwestern rocks and these southern outcrops, and there's an explanation. We firmly believe that these southern and northern outcrops of Precambrian rock were built as separate structures. They may have been separated by an ocean as wide as the present Atlantic when they were building. And it's quite intriguing that our oldest rocks are in the northwest, because the oldest rocks in the world are in Greenland, and before the present Atlantic opened, the northwest of Scotland almost certainly touched Greenland. In fact, our oldest are called Lewisian, after the Isle of Lewis in the Outer Hebrides. And on the mainland, they stretch from just south of Cape Wrath to the south of the Isle of Skye. And they form there a belt of country that is distinctive and most spectacular. Geologists call this kind of rock gneiss, G-N-E-I-S-S. It's very hard and resistant to weathering, and its landscape takes up an unmistakable knobbly form that is characteristic of this part of Scotland. You need the help of a skillful interpreter to understand the history of the rock, because although some of it was originally formed at the surface of the earth, as sediments derived from even older volcanic rocks, it was taken down deep below the surface and subjected to intense heat and pressure for an enormous period of time, about 1,000 million years. I went up to Kinlochbervie in Sutherland to meet someone who has spent a long time unravelling this very elaborate geology, Professor Janet Watson of Imperial College in London.
Somewhere along here, find something worth looking at in detail. Yeah. Yes, what about that?
Oh, that's right. That looks super.
Oh yes, this is fine. Come and look at this, Ian.
This is very different from anything else we've seen.
Yes, it's not at all like your Charnwood Precambrian, is it? Mm. And the reason, I think, is that what we're seeing here are a series of rocks that have been down very deep in the crust. And we're seeing the sort of structures that were produced 30 kilometres down, 40 kilometres down in the crust. Mm. And of course, down there it's hot, whereas up here it isn't at the moment. And the result is that rocks which were, if you hit them at the surface, these rocks simply shatter. Yeah. But down at depth where they're hot and where they're bathed in fluids, instead of shattering, they'll simply gradually distort plastically. And so you get all sorts of weird and fantastic shapes like those ones up there, which are the result of slow distortion of hot rocks.
It's these two colours, the dark and the pale material, that allow us to see all these structures you've been talking about. So what about them themselves? What is the dark stuff and what is the pale stuff?
Well, they're really the two kinds of rock that make most of this Lewisian gneiss complex. The dark stuff here, this is amphibolite, and it might originally have been a basic lava, a basalt or a rock like that, but it's been so modified through the heat and the pressure at depth that it's now not looking like a basic lava.
I see.
And the pale material, your seahorse there, is granite, in composition rather like the Dartmoor granite. But as you can see, it's behaving very differently. The two kinds of rocks here are mixed up together in a sort of way you don't see at Dartmoor. And this again is a consequence of the fact that the whole mass of rock has been down in a very hot, juicy environment where everything has squirmed around like porridge. And the result is you get these very complicated structures, and the two partners in this rock mix with one another in a very small-scale, intimate way, as you see here.
The folding that we can see looks just like a textbook diagram of mountain building, doesn't it? So how does it fit into this whole story?
If we look at that dark layer there, it's going all the way around the core nose of a fold there. It's going right up there, and then quite possibly the same dark layer is coming around this side here, so that it's a very intense kind of folding, and it must represent tremendous changes in shape of all the rocks down there, where they've been subjected to enormous pressures.
Well, with 40 kilometres down and this 2,800 million years old, how do you all this?
Well, we haven't got the usual means of interpreting geological history. Obviously, we haven't got fossils because these rocks are so old. We haven't got ordinary bedding, so we can't see a succession of sediments as we can in Charnwood, for example.
No, no.
So we have to build up a completely different way of looking at the history of these rocks. And if you just take this exposure as an example, here I mentioned these light layers of granite.
Yeah.
We know that granite's an intrusive rock. It comes in as a fluid and then consolidates. So we can say straight away, here are some dark rocks which were intruded by layers of granite.
Yes.
Now we know too that those layers of granite have been folded because we were looking at the folds a moment ago.
Yes.
So there's another stage in the history.
I get it.
Probably somewhere else around this area, we'll find a place where there are some younger layers of intrusive granite which will actually break across a fold. And then you
I
could
see.
say 1 intrusion of early granite, 2, 3 intrusion of late granite.
I see.
And so you can begin to build up event after event simply by looking at the relationships of the rocks as you see them in an outcrop like this.
Yeah, that makes a lot more sense, because usually one looks at this and thinks, gosh, that's just
Just looks
confusing
a
and
mess,
walks on.
doesn't it?
Yeah.
Yes.
But what about the depth thing? Is that going on now at 40 kilometres? Is this sort of thing happening under us?
Not under us, I expect, but it could be happening somewhere else in the earth, in the of the earth,
Yeah.
where there are very deep earthquakes, for example. There must be deformation going on.
Yes,
at
I
depth.
see.
So
Yeah.
perhaps rocks like this are being formed at depth. But on the other hand, there's quite a lot of reason at the moment to think that the kind of phenomena that we see here were going on under larger parts of the continents in the early history of the Earth than they are today. The Earth was hotter, and therefore the continents be at higher temperatures at depth. So that it may be that this kind of activity is going on locally now, 40 kilometres down, but it may have been going on under the whole continent.
So we're
40
probably less
kilometres
active
down.
than
We're
we were.
probably less.
Although the tortured Lewisian Scotland, it isn't the only Precambrian material. After it turned deep below the surface, it came back up to the light of day to form a mountainous. Then the whole area seems to have sunk again. It was Torridonian sandstone, named after Glen Torridon, some. The Torridonian is very clearly bedded and jointed in colour, and it's eroded into steep-sided Sugarloaf Mountain. Perhaps the best known are the unforgettable twin peaks of Sullivan near Loch Inver. As the top slowly wear away, the ancient Lewisian landscape is reappearing, a truly fossil landscape with hills and valleys, forces of erosion 800 million years ago. What is different today is the green veil of vegetation that softens its appearance. A million years ago, when the Lewisian vanished beneath the sand, such plants. There's something secret about this landscape, this unbelievably old skeleton of rocks, miles beneath the Earth's surface and far away across an ancient ocean, that imagination, and makes it, for me, one of the most dramatic and exciting places in the whole of the British Isles.
The time now is coming up to 20 minutes past midday.